my privilege now to introduce our keynote speaker for today, and that's Dr. Vint Cerf. Many of you will know of Vint. He's currently the Vice President and Chief Internet Evangelist at Google. But he's, you know, this is one case where the word pioneer is not an exaggeration. He developed the TCP IP protocols at DARPA, created DARPANet, which, as you I'm sure know, turned into internet. And then, not only satisfied with doing that, he started working at MCI and developing the first email systems. So he's pioneered both the internet and email. Vincent is currently president of the ACM, the world leading computing professional institution. And also, for those of you who may have noticed this year, the Royal Academy of Engineering in the UK has set up a new prize. Looking at the Nobel Prizes and being quite limited to Nobel Prizes, they decided that there wasn't a prize in the world for engineering, a big, prestigious prize. And we set up the Queen Elizabeth Prize, which is presented in Buckingham Palace by the Queen, with a £1 million prize figure. And the first winners of this prize were announced this year, and Vint was at Buckingham Palace a couple of weeks ago, receiving it. There were 5 winners announced. Vint, along with Bob Kahn, his colleague, and then Tim Berners-Lee and Mark Andreessen from the web community. It's slightly unfortunate that the engineering sort of confused the internet and the web again, you know, but whatever. But it was very good to see. I mean, the Royal Academy of Engineering is very much, you know, it's engineering. We're talking about bridges and tunnels and things, so it was fantastic to see them recognizing this as their first prize winner of the Queen Elizabeth Prize for Engineering. So it was great to see that, Vint. And so we're looking forward to hearing you talk about the future of the internet. Who better to tell us this? Thank you.
Well, I always get nervous when people clap before you've said anything. And it doesn't get any better than that, so I feel like I should just sit down. But I will try to. Thank you very much, Larry. That was a lovely, incredibly wide-ranging talk. I'm sure you felt like you were kind of skipping over a lot of depth and detail, but it was very, very helpful as a start. One thing I wanted to mention to you that when you pointed out the huge quantity of information, the petabytes and zettabytes and exabytes and so on, the one thing which I continue to worry about is whether all of those bits will be interpretable over long periods of time. And there's a rant, which I probably won't have time to do today, about bit rot. It's not that the bits themselves disappear. They can be moved from one medium to another, but there's software that's often needed to figure out what the bits mean because they were produced by applications. And if it turns out that those applications don't work anymore because the operating system slipped out from under them, or the hardware that ran the operating system isn't available, so the application doesn't work, the bits become meaningless. And that's pretty scary because I think most of us are, in this early stages of the 21st century, investing an awful lot of ourselves in that digital representation. And so 100 years from now, or even maybe 6 years from now, a lot of this information may be lost. Some of you may have already experienced that with digital imagery and video, for example, where some of the older formats are not interpreted by some of the newer software packages, so it's a big issue. Well, I'm going to try to give you a couple of things. One, I'm going to step back into time just a little bit to give you a sense for the ambition level that was present 30 years ago and how it manifests itself now. So let me start here by going way back in time to the original 4 nodes of the ARPANET. I was at UCLA at the time that this network was being set up in late 1969. Steve Crocker and I and John Postel were all part of the UCLA Mafia. And we also happened to have come from the same high school, Van Nuys High, in the San Fernando Valley. It's just ironic and fortuitous. So I wrote software to connect the Sigma 7 computer to the ARPANET. The Sigma 7's in a museum somewhere today, and some people think I should be there too, but here I am. So this is the beginning of a fairly large-scale packet switch network. And the idea here was to demonstrate that packet switching would actually work. This was not unique to the United States. There was work going on in Europe, and there was in France, and there was work going on in the UK, particularly Donald Davies at the National Physical Laboratory, and Louis Bouzon at IRIA in France. And Louis, in fact, was one of the 5 people receiving the Queen Elizabeth Award, along with Mark Andreessen for the first Mosaic browser, and of course Tim Berners-Lee for his original invention of World Wide Web. So that's where we get started. And of course, this is what a packet switch looked like at the time. It was the size of a refrigerator, and because it was originally commissioned by the Defense Advanced Research Projects Agency, Bolt, Beranek, and Newman that built this decided it should be encased in heavy-duty metal because they knew it was going into hostile territory, a university full of graduate students and undergraduates. So this was packed in this very heavy-duty case. These are, to show you how early and primitive this stuff was, Steve Crocker and John Postel over on the left and I on the right recreated the early stages of ARPANET using squash, green squash and yellow cable. We had this picture taken in the 25th anniversary of the ARPANET. This is in Newsweek magazine in 1994. But the thing I want to point out to you is that you'll notice that this network couldn't possibly have worked because it was ear to ear and mouth to mouth and never mouth to ear. And this was deliberate. We figured it was a geek joke and only the geeks would get it. There we go. Now, one of the things that led to the development of the internet itself was Bob Kahn's ambitious attempt to take packet switching that had been implemented and demonstrated very successfully with the ARPANET using dedicated telephone circuits connecting the packet switches to each other, and to extend that into radio mode. And so we were experimenting with something called packet radio in the San Francisco Bay Area in the early to late 1970s. This was the SRI International Packet Radio Van. And it had essentially, it was completely nondescript, no labels, nothing, and just a stacked dipole array antenna sticking up the top. What I don't know is whether I have another slide here. Yes, here we go. So this was being demonstrated in the late 1970s to the military. The Army agreed to test this in military maneuvers at Fort Bragg in North Carolina, but we had to bring them out for their first religious experience with packet switching in radio mode out in the San Francisco Bay Area. And there's a story that's told that at one point, the engineers at SRI were testing the system, and they would drive up and down the Bayshore Freeway, and then occasionally they'd pull off to the side and stop, and the driver, who's another engineer, would get out and go climb into the back along with everybody else, and they would be doing measurements and testing of the packet loss rates and shot noise coming from the car ignitions going past. One day, a policeman noticed this thing parked down on the side of the highway, and nobody was in the cab, and so he pulls behind it, and he knocks on the door, and the door opens up, and he sees all these geeky guys with beards and computers and displays and everything else, and he says, "Who are you?" And they say, "Oh, we work for the government." And he looks at him and he says, "Which government?" "But officer, we were only going 50 kilobits per second. So this is the inside, and those white things are cubic foot radios. They were using, this is pretty remarkable stuff, this is like 1973, 74. We're running code division multiple access radios operating at 100 to 400 kilobits per second in the 1710 to 1850 megahertz band. These things cost $50,000 each, and we had a bunch of them in the van. And we were even experimenting with packet voice. Now, the ARPANET at the time was running at 50 kilobits a second. Any typical digitized voice stream is 64 kilobits a second. You couldn't put very much voice through a 50 kilobit line. And the packet radio network was going from the packet radios into the ARPANET, et cetera. So we said, all right, we're going to have to do some voice compression. So we used something called linear predictive code with 10 parameters, which models the voice tract as a stack of cylinders that change over time, and they're excited by a formant frequency. That transformation sends just the 10 parameters to the other side, plus the formant frequency estimate. And then that's inverted on the other end. Now, that compresses the voice stream down to 1,800 bits per second from 64 kilobits. Of course, you do lose a little quality when you do that kind of compression. So the consequence of this is that anybody who's speaking through the system sounds like a drunken Norwegian. They're understandable, but so anyway, one day, by this time I'm at DARPA, and I'm trying to figure out how to demonstrate this to a bunch of Army generals. And I thought, okay, how am I going to do this? And then I thought, well, wait a minute. One of the participants in the packet voice experiments was the Norwegian Defense Research Establishment. So I got a hold of Ingvar, and had him be the speaker. So first I had him speak through the ordinary Autovon voice network. Then I had him speak through the packet radio, packet voice system, and it sounded exactly the same. We didn't tell the generals that everybody would sound this way. But just to say that we were very ambitious in those days. Now, of course, voice over IP is quite common, but at this point, it was a very ambitious thing to do. We did similar things with packet video, not much. This was a fairly important date from my point of view because it's the first time that we could demonstrate the interconnection of the ARPANET, the packet radio network, and a packet satellite network, which was using Intelsat 4A hanging over the Atlantic, linking the western part of Europe to the eastern part of the United States. So we basically had the packet radio van running up and down the Bayshore area, radiating packets through a gateway. We didn't know we were supposed to call these routers, so we called them gateways. And it was being artificially, we routed the traffic through the ARPANET, through an internal satellite hop to Norway, down to the University College London, then through another gateway, up through the packet satellite network and back down to the east coast of the United States, through another gateway, and then all the way to the west coast to USC, Information Sciences Institute in Los Angeles. Now, the distance between the packet radio van and ISI in Los Angeles was 400 miles. But the packets went 100,000 miles because they went up and down through the satellite twice and back and forth across the Atlantic and the United States, and it worked. And I remember just leaping up and down saying, it works, it works. You know, look, it's software. It's amazing when anything like that works. So this was a miracle day that showed that TCP/IP would actually allow you to connect 3 very distinct kinds of networks with different packet sizes, different error rates, different bandwidths, and everything else, different variable delay, and actually put everything all back together again on an end-to-end basis. So for us, this was a very exciting moment, one which persuaded us it could work. Now, of course, this is what the internet looks like now. This is actually generated automatically by looking at the global routing table, which has about 400 to 500,000 entries in it. Every one of those entries makes reference, in effect, to an autonomous system, which for all practical purposes you can think of as a network. Sometimes there's more than one network operated by the same company, but each one of these things represents an independent network which is interconnected at an inter-exchange point or sometimes direct interconnection among the networks. But what's important about this picture is that it's not centrally controlled. This is not a single top-down organization that structures and organizes everything. It is completely bottom-up. The people who run these networks choose what software to run, they choose what hardware to run, they choose who to connect with, on what terms and conditions. And the ensemble works because of the standardization of protocols on an end-to-end basis and within the interior. So the idea that it's possible to make something like this work without central control is rather surprising. Most people who would set out to try to do this would look at, if I walked into any venture capital operation and said, here's what we're going to do. It's going to be this big, and it's going to have 400,000 networks in it and about 3 billion users, and it will run on the speeds of 50 to 100 gigabits per second in the backbone, and it'll only take us 30 years to get there. You know, the answer would be, see you around, really great, you know, and when you get off the mescaline, let me know. So this is a gigantic and global collaboration, and the fact that it works is something of a surprise, but it shows the power of wanting to be part of a common environment where everything is connected to everything else. So these are old statistics, and the outfit that I got them from doesn't seem to be producing any new ones, so I'll have to find some new sources, maybe the ITU, but the numbers are, magnitude are correct. There are at least 1 billion, probably more than that, servers in the internet today. These are machines that have typically an IP address and a domain name that is fixed. Now, in fact, many of these things are hiding behind the edge interfaces into a cloud, which is increasingly the most common way of providing service on the net. So the real numbers are much, much larger than this in terms of devices connected to the net. On top of which, there are a lot of devices that are episodically connected, laptops, desktops, mobiles, tablets, and so on, that are not necessarily always on. So the real number of things that are able to connect in the network, even if they're not all connected at the same time, is surely numbered in the several billions. And as the Internet of Things happen, as Larry points out, those numbers will get bigger and bigger. The number of users as of last year was about 2.4 billion. Today it's probably closer to 3 billion. The number of mobiles that are out there is 6.5 to 7 billion. Not all of them are smartphones, so not all of them are really internet capable, but probably 20 to 30% of them by this time, and surely over time that number will increase simply because it's hard to build a machine that isn't internet enabled anymore just because the chipsets sort of come with all the right things. So these numbers continue to grow over time. They do give a certain amount of motivation, though, to the chief internet evangelist who wants all 7 billion people in the world to be online. So I have about 4 billion people to convert, and I could use some help if you're interested. Here's where the people are, and the only reason I put this up is to remind you that Europe and North America, that used to be the largest concentrations of internet users, have now been eclipsed by countries in Asia, especially China, which now has a reported 650 million people online. And so although we hear all kinds of stories about hacking and censorship and blocking of various things, all of which are true, about China, they're also investing very, very heavily in the internet. And so there's going to be an interesting thing to watch the impact on that society as time goes on. And my guess is that all of the efforts to suppress free exchange of information in China will eventually erode simply because of the presence and existence of all of the things that are online and accessible to the Chinese population. The rest of the data is as you see it. Africa continues to be a big challenge because of the still relatively immature telecom infrastructure, but even there, we're seeing an extremely rapid growth of mobile. So for many, many of the people in that continent, the first interaction that they'll have with the internet and its applications will turn out to be on mobiles, and it may stay that way for quite some time. Eventually, I think that they will have to catch up. They will need higher bandwidths than we can typically supply with today's radio technology, although there are some very interesting speculations of getting out into the 60 gigahertz range, which has the interesting property that it is in the oxygen absorption band, which means if you transmit at 60 gigahertz, the signal just literally gets absorbed in about a half a mile, which makes it great for reuse of that frequency. So in some interesting sense, you could get many gigabits a second at 60 gigahertz and reuse the frequency fairly easily as you get base stations that are repeating the signal without necessarily much interference. So Larry's already mentioned most of this. One thing that's sort of embarrassing is that we didn't get the address space right when we started. But I want you to imagine, you go back 40 years, literally, to 1973. Bob Kahn and I are sitting here saying, how the hell are we going to get this stuff to work? We have an arbitrarily large number of networks. We just sort of finished building the ARPANET, and it was reasonably large scale, covered a lot of the US plus parts of Europe. And so we said, well, this is not an inexpensive thing to do, to build a national scale network. So we thought maybe there will be 2 per country. So there'll be some competition. Then we wondered how many countries are there, and we didn't know, and there wasn't any Google to ask at the time. So we guessed that it was 128 because that was a power of 2, and programmers. So we said, all right, let's see, 2 networks times 120, that's 256, that's 8 bits. And then how many computers per country? And we thought, at that time, remember that computers were big time-sharing machines that served typically 1,000 to 10,000 people and cost millions of dollars and occupied multiple rooms and air-conditioned and everything else. But we thought, let's be generous, how about 16 million machines per network, which is 24 bits, so that's where 32 bits came from. And we even debated this at one point about 4 years later in 1977, should we have 100, somebody actually suggested 128 bits. Now, look, I'm the program manager at ARPA, right? Somebody's saying, we need 3.4 times 10 to the 38th addresses to build this experimental network. And I'm sitting here thinking, that doesn't pass the red face test. I can't explain to anybody in the Pentagon, let alone the Congress, why I need 340 trillion addresses to try an experiment. So we stayed with 32. And we did pretty well with it because we didn't run out till 2011. And IPv6 was actually designed, and some people implemented it as far back as the late 1990s. But it hasn't been taken up very quickly, but now we've officially run out. There is an auction that's growing right now for unused legacy IPv4 addresses. At some point, it will become too expensive to play around with v4 and it will be much smarter to get a whopping big chunk of IPv6 and just run with it. So you can help, though, if you go to your internet service provider and ask them, what's your plan for rolling out IPv6 and when can I get my addresses? And you know, pound on the table and insist on it. They'll get the message that somebody cares, because right now they think nobody cares about IPv6. The thing is, no normal user should ever even know that there exists IPv4 or IPv6. It all gets mapped from domain names. But some of the ISPs, maybe some of you are in this room, are waiting for somebody to tell them they should do that. I'm telling you to do that. It's okay, so get busy. The other thing that's happened is that the domain name system, which used to be all Latin characters, you know, A through Z and 0 through 9 and hyphen, are now outfitted with non-Latin character sets drawn from the Unicode set, which is also used in the World Wide Web. So now you can have literally thousands of different languages that are represented in domain names, and that process is underway. The Internet Corporation for Assigned Names and Numbers, as all of you must know, has opened up the top-level domain space now. 2,000 people applied for possible top-level domains at $185,000 per application, so we're talking $350 million, which is a fairly big kitty to have put away in less than a week. That process is also underway. Some of it's internationalized, some of it is still Latin characters. And there are lots of issues arising about who's allowed to use .Africa or .Patagonia or other kinds of sometimes trademarked names, or names that are of places that countries would like to feel like they can protect and own. On the other hand, there are counterexamples, .Asia being a good example of one where everybody agreed that that was an okay thing to do, and so that was introduced, in fact, some time ago. The other thing, which I think is very important, security came up in Larry's comments, and that is that when the original design was being done and standardized around 1978, the state of security apparatus and technology was still limited to mostly classified stuff. Certainly in the US. And so although a design was done with NSA, in fact, on a secured implementation of the internet, it used technology that was classified, and I could not share the architecture with my friends who didn't have clearances. So we sort of went down this parallel path. And ironically, two of my colleagues at Stanford, Marty Hellman and Whit Diffie, invented public key cryptography and published a paper in 1977. And for those of you who are geeky enough to pay attention to this, GCHQ actually discovered public key cryptography in 1974, but they didn't tell anybody for about 30 years that they had encountered the same notion. Well, unfortunately, Whit and Marty didn't actually implement it. They just wrote a paper about the existence of this. So by 1978, I was standardizing the TCP/IP protocols, and we lacked availability of public key crypto. All we had was the standards, symmetric key kinds of stuff, and it was still classified. Today, however, there is an ample amount of very high-grade crypto capability available. You can license it from companies that include elliptic codes, for example. And so we're putting in and retrofitting a lot of this capability to the domain name system itself, into the routing system as well, digital signatures to bind IP addresses to domain names, digital signatures to bind IP addresses to autonomous systems and to owners of internet service. So all that stuff is going on. We have an opportunity to make a much more secure network. We can use two-factor authentication and public key crypto and other things in order to help people make more private and more protected and more confidential the information that they are using. The other three bullets here just are to say that other things are happening that surround the edges of the net, sensor networks, for example, and the Smart Grid program, which is all about electrical devices that both take and give, take advice and give information, which Larry alluded to as well, is also underway, and of course mobiles all over everywhere. So, yeah, this is some of you may remember Dr. Seuss. He made sculptures, and so I bought this one, and it seemed to me, this seemed to be what he was saying, and I hope all of you will take that to heart. These data probably come from some of the data that Larry also showed, so I won't belabor the point except to say that Larry's YouTube thing is out of date. You said 60 hours of video are being uploaded. It's 100 hours now, and probably the number is increasing. I have no idea who watches all that stuff, but Somebody said that the number of people that look at blogs is approximately 1.4, the author and his dog. That's on the average. Now, some blogs are more popular than that. Again, this is more statistics giving you a sense for the level of activity in this environment. It really is quite astonishing when you realize how many devices are capable of either generating or absorbing and doing something with or allowing you to interact with content on the network. My rendering of the Internet of Things looks a little bit like this. Well, I remember I've been watching this for 40 years now. We turned the Internet on January 1st, 1983. So this year we had its 30th anniversary. Although pieces of it have gone down from time to time, the whole network has not gone down in 30 years, which is pretty amazing, especially considering the growth rate and the level of attacks that go on day to day. I remember somebody ran into my office probably in the 1990s saying, Vint, did you see the Internet-enabled picture frame? And I thought, that sounds about as useful as an electric fork, But actually, these turn out to be very, very useful. We use them in our house, too, and you must do this as well. We all have mobiles with digital cameras in them, so we all take pictures. We upload them to a website. The picture frames download them from a website. And that means you can watch the grandchildren and the nieces and nephews and so on. You get up in the morning and look at the picture frame to see what everybody's doing. Of course, this does emphasize the importance of security, because if somebody hacks the website where the pictures are supposed to be, then the grandparents are going to see pictures of what they hope are not the grandchildren. So this makes security just as important at home as it is at work. There are other things like the Internet-enabled refrigerators. The high-end refrigerators have these lovely high-resolution, touch-sensitive displays. This is what the Americans use to augment their normal communication system, which is magnets and paper on the front of the refrigerator. Now we can do websites and blogs and things like that. I used to wonder, what else could an Internet-enabled refrigerator do? And I thought, well, what if you had an RFID chip on everything that goes into the refrigerator and a little sensor? So the refrigerator knows what it has inside. So while you're off at work, it's surfing the Internet looking for recipes that it knows it can make with what it has inside. So when you come home, you see a nice little list of recipes that you could do for dinner. You can extrapolate this. You might be on vacation. You get an email. It's from your refrigerator. You put the milk in 3 weeks ago, and it's going to crawl out on its own now. Or maybe you're shopping, and your mobile goes off. It's the refrigerator calling. Don't forget the marinara sauce. I have everything else we need for spaghetti dinner tonight. Now, unfortunately, the Japanese have messed the whole thing up. They have an Internet-enabled bathroom scale. You get on the scale, and it figures out which family member you are based on your weight, and it sends that information to the doctor. It becomes part of your medical record, all of which sounds perfectly reasonable, except for the fact that the refrigerator is on the same network. So you come home and you see diet recipes coming up on the display, or maybe it just refuses to open because it knows you're on a diet. So maybe this is not a good idea after all. Now, of course, mobiles are in the picture as well. The guy in the middle is the one I like. This is an Internet-enabled surfboard. I haven't met him. I think he's Dutch. And I can imagine him sitting on the water waiting for the next wave, thinking, if I had a laptop and my surfboard, I could be surfing the Internet while I'm waiting for the next wave. So he put a laptop in the surfboard, and he put a Wi-Fi service at the rescue shack back on the beach. Now he sells this as a product. So if you want to, be out on the net while you're out on the water, this is the thing for you. Then I used to tell jokes about someday every light bulb will have its own internet address, and I thought, haha, that was funny. Somebody sent me an LED, internet-enabled radio light bulb for about $20. The radio and the IPv6 chipset cost about 50 cents, which is not a bad, addition to the basic cost. And since it's an LED light bulb, it lasts for 15 years. So this is actually not a crazy thing. You can turn it on, turn it off, test its current condition remotely. And finally, of course, there's Google Glass is another example of the sort of thing that's going on. And here I wanted to draw your attention to the consequences of drawing a computer into the same environment that you're interacting in. So the computer is seeing what you're seeing, and it's hearing what you're hearing. And so it has context for anything that you might want to do using its resources. So I could be pointing to a bottle of wine, saying to Google Glass, what are the tasting notes for that bottle of wine? And of course, I'm looking at the label, and it sees the label, and it can take a picture of that and go search for that in Google Goggles, for example. Then do a lookup in Cellar Tracker, for example, and come back and tell me what the tasting notes are. Or here's another example. We can't quite do this, but we can get awfully close. Imagine that there is a blind German speaker and a deaf American Sign Language speaker, and they're both wearing Google Glass. Let's see what happens. So the German blind speaker speaks German. Of course, the deaf guy doesn't hear him, but Google Glass hears it, figures out how to recognize the German, translate the German into English, and show the English as a caption display for the blind guy to see in the Google Glass. Now the deaf guy starts signing. And of course, the blind guy can't see that, but his Google Glass can see it, figures out what the signs are, translates those into English, translates the English into German, and then speaks the German in the earpiece, or actually it's a bone conduction interface in Google Glass, so the blind guy can hear what the deaf guy was signing. Now, we can actually do all of that except for the signing part. And I think that's entirely feasible. Maybe not yet with video, but there are some gloves that people can wear that you can sense the position of fingers in. You may actually get very close to doing ASL interpretation that way. So this idea I find very exciting of bringing a computer into the normal environment that we're in. It can hear what you say as well. So there's voice interaction. There's the possibility of looking at something and asking, what's that? Or, asking for directions and having the display show up. Or, where's the nearest Thai restaurant? Can I see the menu? There's just a variety of possibilities here. And because you're hands-free, it really is quite a remarkable experience. I would have brought my Google Glass with me, but I've left it behind in my apartment in London. But next time I'm here, I'll make sure to have it on. So that's sort of the kind of thing, the environment that we're in these days. Now, this is another example of a sensor network I have in my house. It's an IPv6 radio network, and it's a commercial product. This is not me in the garage with a soldering iron. In fact, it was made by a company called Archrock, which was acquired by Cisco Systems. The little devices are about the size of mobiles. They run on 2 AA batteries for almost a year. They're sampling temperature, humidity, and light levels in every room in the house. And every 5 minutes, they report this information through the radio network to a server down in my basement. Each of these sensors is also a relay. So this is a mesh network, which is running on little batteries. So one of the rooms is the wine cellar. And of course, I'm concerned about the temperature there. So if the temperature goes above 60 degrees Fahrenheit, I get an SMS on my mobile telling me that, that we've just broken through the temperature barrier. This has happened a couple of times, especially when I've been away. And I didn't have any way of remotely resetting the cooling system. In the particular case, my wife was away on some other holiday. So I asked the Archrock guys if they made remote actuators, and they said yes. So that was a simple weekend thing. And I said, by the way, do you have strong authentication? Because I have a 15-year-old next door, and I don't want him messing around with my wine cellar. And so they said yes. So we have a strongly authenticated system, and the wine cellar now is capable of keeping track of temperature, humidity, and light levels, which led me to think, gee, I can actually tell if somebody's gone into the wine cellar when I'm away, because I can see that the light has gone on. Of course, I don't know what they did in there. So this brings me back to the RFID idea. What if I hung an RFID tag on every single bottle? Then I could do an instantaneous inventory to see if any wine has left the wine cellar without my permission. So I actually had somebody come out with a prototype of an RFID handheld detector. We walked through the wine cellar, worked great. So then I got to thinking, this is really a pretty nice thing. I was boasting to one of my friends about this great engineering design for making sure that my wine was properly handled. And he said, there's a bug. I said, what do you mean there's a bug? He says, well, you could go into the wine cellar and drink the wine and leave the bottle. So now we have to put sensors in the cork. So I thought, all right, well, if I'm going to do that, I might as well sample the esters to figure out whether the wine's ready to drink. And so before you open the bottle, you interrogate the cork. And if it turns out that was the bottle that got to 75 degrees or 80 degrees or something, that's the bottle you give to somebody who doesn't know the difference. So this is a very practical thing to have around the house. In all honesty, I expect these things to be very normal. I think many buildings will have instrumentation like this for environmental control, for security, and for a variety of other purposes. So this, too, is a growing part of the internet environment. This, of course, is the self-driving cars at Google. Larry and Eric and Sergey are pretty excited about this. It's a Google X project. But you know where this came from? The Defense Advanced Research Projects Agency, again. They wanted to see if people could build vehicles that would drive themselves for military purposes. Well, the first year that they did this, they had, I don't know, maybe 15, maybe not even, maybe 7 contenders, and all of them ended up in the ditch within a few miles of the beginning. That was the first year. Second year, 7 people made it all the way to the end of a 127-mile course out in the desert, and the winner was Stanford University with the Stanford Steamer. The next year, the challenge was an urban setting. So, and again, a number of contenders brought their self-driving vehicles. We couldn't find anybody to serve as pedestrians in that test, though. But we had the vehicles driving around, and Carnegie Mellon won that time. So Google, of course, hired the Stanford team and the Carnegie Mellon team, and so now they're working at Google X on advances in self-driving cars. We've driven a fleet of about 24 cars, 500,000 miles in the city of San Francisco, with no accidents. There was one accident, but the car was being driven by a human being, the automatic thing was off, and somebody rear-ended him. So that doesn't count. One thing which was very interesting is the difference between getting a car to drive on the city street, where it's trying to recognize lines and where are the street lights and so on, and driving door to door, because that's different. Door to door means navigating in underground parking garages or figuring out how to find the front door of the house and so on. And so we're finding, as we challenge ourselves to do this sort of door-to-door capability, that it's getting harder and harder to make this work. But there are several states in the US now that have officially passed laws allowing these cars to be driven on the roads. Now, one thing I should tell you is that you don't anticipate getting into a car like this and drinking yourself into a stupor in the back seat. And the reason for this is the car is smart enough to know when it doesn't know what to do. And so there's an audible sound when it says, I'm turning the car back over to you now. So it's not good if you're asleep in the back seat. You need to stay in the car and be ready to take over if necessary. I'm going to skip through the smart grid stuff, and partly in the interest of time and partly because I want to get some Q&A bit here. Just a light comment about this is a list of major issues that are affecting the internet. It has less to do with technology than it has to do with policy. And the policy ranges over fairly large-scale things like who's in charge of the internet, what does internet governance mean, struggles by the International Telecom Union to somehow expand its mandate beyond its historical telegraphy and telephony roles. Many of us pushing back on that, believing that that should be done by other parts of the Internet Standards Establishment, the Internet Society, ICANN, the Internet Engineering Task Force, and the like. So there's still a good deal of debate about that. Privacy and safety and security are all big issues, as you can tell. I'd like you to concentrate for just a moment on the word safety, though, because I think most people are concerned about feeling and being safe on the net. They worry about viruses, worms, denial of service attacks, exposure of private information, all kinds of things of that sort. Some of these things are not necessarily violations of law. They're more a question of attacks against the system or even mistakes and bugs. And this is one of the big issues for me, is that some things go wrong in the net because of an accident. It's not somebody who deliberately disabled something. They just made an accident, misconfigured a table, and half of the network goes away. So I would like to concentrate on safety for a moment. Imagine that a lot of small and medium-sized businesses don't have an IT department that's prepared to help clean up a problem with an infected machine or an internal or external denial of service attack. We don't have cyber fire departments anywhere right now, and I think we should start thinking about that. The image I have in my head is that you're standing in front of your house, and the house is on fire, and you have a garden hose, and you're thinking, I need somebody with a bigger hose and more water. And you don't call the fire department, or the police department, you call the fire department to put out the fire. Then after they have put out the fire, of course, then they have to figure out, well, where did the fire start? And maybe that's when you call the police department because they discover arson in some cases. But it's not the first thing to do to call the police department. You call the fire department. I think we need a cyber fire department. We should be experimenting with that. And I also am concerned about anonymity and strong authentication. I think that people should be able to be on the net in an anonymous or pseudonymous way. A lot of people will argue that this is bad because if you are not known, if you're pseudonymous or anonymous, you'll say bad things, and that's true. Some people will do that. But there are other circumstances where anonymity is important for protecting safety, protecting life and limb, for reporting something that's improper going on somewhere, whistleblowing and things of that sort. So I think that we have to countenance an environment in which all of these things are contemplated, including strong authentication, because there are some transactions where it's really important to know who the parties are. I mean, if I'm engaged in a financial transaction, I really do want to know who is the other party, and if they renege on some part of the agreement, I have a way to get to them legally. So that's important. I mentioned the bit rot problem, and the term for solving it is digital vellum, and I don't mean by this just physical medium. I mean the entire ecosystem that's needed in order to continue to interpret bits. I have just a little bit more here and then I'll stop. I want to skip through that too. Okay, so I figure I owe you a quick update on an interplanetary extension of the internet. And when I started briefing this in 1997, everybody thought I was telling a joke. This was actually a project that was started at the Jet Propulsion Laboratory in 1998. We began by asking ourselves, what about the planned missions that were going to Mars in the future? And many of them have already landed, like the 1997 Pathfinder project landed on Mars successfully. Then the 2004 rovers, 2 of them landed there. The Phoenix lander in 2008, and now the Mars Science Lander last year. So what's very exciting to us was the idea that we could build rich networking capability to help support manned and robotic space exploration in the solar system. And we thought that at the beginning that we might be able to get away with things like TCP/IP, except we discovered quickly it didn't work very well. It works okay on Earth, and it would work fine on Mars, but it doesn't work between Earth and Mars because of the distances involved. It's 35 million miles when we're closest together, 235 million miles when we're farthest apart in our respective orbits. That's 3.5 minutes to 20 minutes of radio propagation at the speed of light one way. And of course, round trip is double that. Flow control with TCP was designed to be very simple. I run out of room, please stop. And if you say that and it takes a few hundred milliseconds for the other guy to hear, everything works okay. But if it takes 20 minutes before they hear you say, I've run out of room, they're sending data at maximum rate, the packets are falling all over everywhere, and you lose a lot. So flow control doesn't work very well at these kinds of distances. Then there's celestial motion. The planets are rotating, and we don't know how to stop that. So if you have something on the surface of the planet, it's talking to you, and the planet rotates, eventually you can't talk to it until it comes back around again. And the same is true for some of the orbiting satellites. So what we're faced with in this interplanetary environment is variably delayed communication and disruption. So we invented a whole new suite of protocols, still packet-based, but they're called bundle protocols, and they are prepared to deal with these really major problems in interplanetary communication. They're now in operation on the International Space Station, on planet Earth, on Mars, on the rovers and in the orbiters, and also in a spacecraft called Epoxy, which is in orbit around the sun and has visited 2 comets in the last decade. So we actually have an interplanetary internet in operation today. We're standardizing those protocols through the Consultative Committee on Space Data Systems, and what we're anticipating is that once the standards have been adopted this year or possibly early next year, that any of the spacefaring nations of the world will be able to use those protocols so that all of our spacecraft will have some compatibility. And even if they don't use the protocols for the primary mission for which the spacecraft has been assigned, when that spacecraft has completed its primary mission, it could be repurposed as a node of an interplanetary backbone. And so you can imagine over a period of decades literally growing an interplanetary network over time. Now the interesting thing is that this whole vision does not stop there. Here's the next part. We're back at ARPA again. ARPA just funded a study to design a spacecraft to get to the nearest star in 100 elapsed years. Now, there are a few problems associated with this. The first one is propulsion. the current propulsion systems would take 65,000 years to get from Earth to Alpha Centauri, 4.4 light years away. That's a little long even for an ARPA project. So the first problem is propulsion. Our expectation now is an ion engine of suitable capacity could accelerate the spacecraft to 20% the speed of light over a 50-year period, at which point we would flip over and decelerate, because otherwise we'll go zipping through the Alpha Centauri system at 20% the speed of light and get one picture, and that's probably a pretty expensive picture. So the idea now is to deal with the propulsion with probably an ion engine. The next problem is navigation. And normally when you send a spacecraft off somewhere in the middle of it all, you do mid-course corrections in order to get it into the right trajectory. The problem is, what if you have a spacecraft that's a light year away? It takes a year to tell it what you want it to do, and it's a year before you find out what happened. So this is not exactly, interactive. So we're going to have to do autonomous navigation in the spacecraft, and that's probably okay because we know what the trajectories are of the suns that are within 10 light years of Earth, and we know that stars that are much farther away in the galaxy retain their configuration even if you move 4 light years away. So we can use that to orient the spacecraft and then let it autonomously figure out how to adapt its trajectory. So that part's easy. The last part is communications. How do you generate a signal that will be detected from 4 light years away? This is on a spacecraft that you have to have, whose mass has to be appropriate to get there in 100 years' time. So it can't be terribly massive. Some of us have been thinking about using collimated lasers, and one possibility is what's called a femtosecond laser. This is a laser that does pulses that are 10 to the minus 15 seconds long. So if you had a 100-watt power source, you could compress the signal down to 10 to the minus 15 seconds, which is a really whopping big signal. It's a big spike. And that should be detectable except for one problem. Even though it's a collimated laser, by the time you go 4 light years away, the beam has spread to the size of the solar system. So it means it's very attenuated. So now the question is, how do you detect that? Now you know why I need the interplanetary backbone. I want to build a synthetic aperture receiver the size of the solar system in order to reintegrate the signal coming back from Alpha Centauri. But one of the physicists has suggested another solution to the problem. He reminds us that gravity bends light. You remember that Einstein's theory was partly demonstrated by the bending of light during a solar eclipse. It was a star, I guess, that looked like it moved exactly as much as Einstein predicted it would, thanks to the bending of the sun's gravity, the bending of space because of the sun's gravity. So it turns out that the sun's gravity can act as a lens. So if you go 550 astronomical units away from the sun, that's the focal plane of the sun's gravity lens. Now that's 55 billion miles. And the Voyager spacecraft have only gone 13 billion miles, and it's taken 33 years to do that. So we have some work to do to get a spacecraft that far away, but that would be a great test for the ion engine to begin with. So the proposition now is to put a spacecraft at the appropriate location, 550 AU away, and then use it and the sun's gravity to capture the signal coming from Alpha Centauri. So that's up to the date on the interplanetary and the interstellar system. I thank you for your time, and I'm happy to answer questions. Wow.
We've just got a few minutes for questions because I promised Vince he'd get out of here at 5:30. So, burning questions, Wendy, yeah?
Yes, ma'am. Actually, we have a microphone coming so other people will hear you. There you go.
Shared spectrum.
Yeah.
As an architecture, tell me when you think that'll be commercialized and en masse.
Oh gosh, I wish that I could give you I'm dying to do that. It drives me so crazy to see these narrowband allocations of spectrum in dedicated purposes when we know about radio propagation. We know we can generate very complex signals. We have receivers that can decipher the codes and the polarization and all these other things that we know how to do. Every time we try to do this in the US, the FCC makes very tiny little steps. Here's what I think. I think that the military is the place to do this. They have spectrum available, which is not available to the general public. We use that same spectrum, 1710 to 1850, for example, or 1855, to do the packet radio program. And if that spectrum could still be available, part of it anyway, I'd love to be able to use it, but I really want to get up into the 60 gigahertz band because there's so much more bandwidth available. So the honest answer to your question is, it will probably take at least 5 years to get a good, solid research program in place, and then commercialization has to come after that. So I would not say that you should be saving up your dollars to make an angel investment in the near term for that. But we have to do something about this. It is just silly the way we've done this. The reason we're doing it the way we do now is because we're all using an allocation system that was designed for 1916 radios that had crappy receivers. They were just wide open receivers. Any signal at all was sucked in. And the result, of course, was that we had to do very narrowband things and control transmission. If we're careful and smart, we'll control reception in addition to controlling transmission and make it possible to share all that capacity. But if you would rant and rave some more in public, that would be really helpful. All right, next question.
Over here.
Well, over here, all right.
Sorry, I've got to ask this, but you mentioned the internet is a wonderful bottom-up network with no central point of control. Do you think the New York Times is regretting that?
So interestingly enough, they probably, first of all, I'm sure they regretted not locking down their registration. That's really what happened. The registrar was penetrated by somebody playing a fishing expedition, figuring out how to get access to the registrar's control over that registration, and then changing the IP address. If that had been on registrar lockdown or registry lockdown, the problem would not have happened. So this is a really good example of the need to help educate people who are using the internet and have responsibility for portions of a company's or a country's assignments to take the necessary steps to make sure that things are in fact more controlled than they have had to be in the past. So the honest answer to this is no, I don't think central control would have made a heck of a lot of difference. I do think, though, that practices, good hygiene, for example, would have made a very big difference. And I'm sure that they're on register lockdown now. In fact, the last reports I heard was that that's what the registrar, Melbourne IT, did automatically for them. They locked it down for them because they hadn't asked for that. But if any of you are holding registrations, you should go and make sure that you have it locked down so nobody but you can make any changes. Okay, next question.
Last question.
Okay, yes, sir.
You talked about the importance of PKI.
Yes.
But obviously that had a surge of interest and then that kind of died away again. So why do you think it really didn't gain hold previously, and what do you think is different now?
Okay, I'm going to make sure I've understood the question. Why do I think that PKI is applicable or appropriate now? Or?
No, previously people like VeriSign were pushing PKI.
Oh, yeah,
big,
okay.
And lots of people were really excited about
Right.
it, and then adoption was really low.
Okay, well, they have whatever reasons they have. Here's what I think. First of all, PKI is a very powerful tool. This certificate authority idea is not working. And the reason for that is there are too many of them, and there are too many of them in your browser, and your browser doesn't know which one is, in fact, compromised. So statistically, it's sort of like, the death statistics. We know that X number of people will die between the ages of 50 and 60 tomorrow morning. We just don't know which ones. So you don't necessarily know which ones of the certificate authorities have been compromised. There's an alternative design, which goes under the name DANE, D-A-N-E. It's being pursued in the Internet Engineering Task Force, that involves using DNSSEC, which is the digital signing of entries in the domain name system, to incorporate the certificates, or at least the public keys, bound to the IP addresses inside the DNS itself. The thing which makes the certificate authority idea weak is not just the possibility of compromise, but in the current formulation, any certificate authority can sign any string bound to a particular public key, any string, which means that anybody who can find a certificate authority that's willing to be compromised could obtain a string that says www.microsoft.com or google.com, and then use that digital certificate in order to force somebody's update software to believe that the update is valid. So the problem here is scope of what the certificate authorities are allowed to authenticate. When we go to this DANE architecture, the only thing you can bind to the public key is something that's in the zone of the domain name system that's digitally signed all the way down to whatever the level of that domain name is. So you confine the potential danger and hazard of a compromise to just that part of the domain name space, not to arbitrary parts of the domain name space. So that's one mechanism that I think should be adopted in order to confine and limit the potential damage. I still think PKI is a very powerful tool. Okay, is that all the time we got? Oh, too bad. All right. Thank you. I appreciate it. Thank you all.
So that's it for this afternoon. I hope you'll join me in thanking Heidi and Eddie, Karen, Wendy, and John, and Larry, and Vint. Thank you very much. Now, we've got to get out of here because we're going to reset the place for dinner, and I'll see, I guess, a lot of you tonight for the Young Software Year. Do you want to say something, Polly?
Okay. Remember, we're not here for dinner. We're at the museum for dinner.
Oh, sorry.
There is a dinner here. I'd hate you to turn up here and not get a place.
Okay.
Those of you who are joining us for dinner, it's at the Royal Museum of Scotland in Chambers Street, and we look forward to seeing you there from 6:30.
It was just as well you said that.
I know.
Thanks a lot.